So I will start directly with the problems, and while solving the problems, we will learn various strategies and. So is this problem visible? Okay. Try this problem for some time, then I will give you a hint. And in the meantime, if you get any idea or like if you find the solution, just tell. Any ideas? So suppose this is how you have to color it. And now look at all these cells which are supposed to be colored black finally. So how many of these cells can you change to black in 1 at most? Like right now the board is entirely white, and now finally you want these cells to be black, right? And suppose you perform an operation on this row, then maximum how many of these cells can become black? Yeah, so maximum 50 can become black, right? So in any particular move, you can make at most 50 of these squares black, and the total number of squares you need to make black is 50 into 100. And so you will need at least 100 moves, right? Now try to find a construction because of which you are able to achieve this kind of coloring in exactly 100 moves. Also, like, it's a problem solving session, so if you have any partial ideas, then also it's okay, just like it will be more helpful if it is a bit interactive. So try to think how can you color these cells. Maybe try it for smaller cases first and then try to generalize the construction. That is also like, for example, let's try it for a smaller case.
So this makes sense because it means to like color one cell and we can select the cells.
Sorry, you are not audible.
In 2x2, we can easily do that. Right?
Are you able to find a construction for this?
I'm fine.
Sorry. Okay, sure. Maybe try construction for 6 by 6 first, or 4 by 4, anything.
Yeah. Can I like annotate? I think I found a construction.
Okay.
Can you show the problem once more?
Oh yeah. So the cells of a 100 by 100 table are colored white initially. Now in one move, it is allowed to select some 99 cells from the same row or column and recolor each of them with the opposite color. Like if the ones which are white, you have to color them black, and which are black, you have to color them white.
But like initially everything is white, so
Yeah.
yeah.
And what is the smallest number of moves needed to get a table with a chessboard coloring? That is alternate white black.
Okay.
So the first thing we did is, so suppose we are going to end up with a coloring like this. So now the cells are going to be alternately white and black like this. Now consider the cells which are finally going to be black. Now in any operation of a row or column, you can make maximum 50 of these black, right? And so you will,
Yeah.
and now there are total 15 to 100 black cells squares. So you will need like at least 100 moves to get this kind of coloring. And so now the claim is that you can do such a coloring in exactly 100 moves. And so for that, you have to come up with some kind of construction.
Okay. Thank you.
So, did you find any construction?
Yeah, I'm trying now.
I think I found one construction.
Okay.
Oh, I don't think I can annotate. And I can't screen share. Should I just like, how should I describe the construction?
Okay, so you want to screen share?
Yeah.
Okay, sure.
Oh, you cannot. Okay. Okay, good. Okay, it's now green. So what I did is like, so for like each of these, like, having trouble drawing. Each of these rows and columns,
Okay.
the 99 squares that I colored or that I switched were the ones that were not on the diagonal here.
Okay.
So
So you colored each of these rows and columns and left the squares on the diagonal, right?
yeah,
Okay.
should I show that it works?
Yeah.
Yeah, so like we can start by coloring like this one. Right, so I colored all the ones that are not on the diagonal. And then we can do like this row or this column. And then I skip this one and I uncolor this one. And then similarly,
Yeah. So your idea is great.
yeah, and then you can just continue
Yeah.
that one.
So the thing is, all the squares in this diagonal are going to remain white since we are never going to color those. Now, okay, so let Can you just label the rows and columns?
Sure. I'll go like, purple.
Okay, so let the leftmost column be the first one and the uppermost row be the first one. So now he is going to color all the odd columns and rows, and
Yeah.
and so now if any square is in an odd column and odd row, then it is going to get colored twice. And so it is going to finally remain white. For example, um, the square with the coordinates, the third square in the bottommost row, and all such squares which are there in the intersection of odd row and odd column. Whereas the squares which are in the intersection of odd row and even column, they are going to become black because they are going to be colored exactly once. And so in this way, we are going to get an alternate black and white coloring. And like this is the construction for a 6x6 board, but we can like easily generalize it to a 100x100. And so in this way, we can achieve the coloring in exactly 100, which is the minimum. Did everyone follow?
Yeah.
Okay.
Yes.
Yeah, very good. So let's try another problem. Sorry, just a minute. Yeah, so here's another problem. So Alice has 100 sets, and at each step, Bob can choose two distinct sets of them, and Alice tells him the intersection and union of those sets. Now find the least steps that Bob can find all of the sets. Like the least number of questions Bob has to ask. Oh, you cannot see the screen?
It's visible.
Okay, so then maybe he had some internet. Maybe first try a few small cases and try guessing that.
For two sets, it's not possible to guess. So trying for three. Yes.
Can you repeat?
I'm saying for two sets, it's not possible. So we should try for three sets.
Yeah, okay.
But can I tell?
Yeah, sure.
So we can for three itself. For n is equal to 3.
Okay.
Yes.
We have three sets A, B, and C.
In these three moves, we can know A union C, A intersection C, A union B, A intersection C, and B union C, and B intersection C.
Okay, so you are going to find all these three.
Yeah.
Okay. So now if you do these moves, are you able to determine A, B, and C?
Yes, we can.
Okay.
Can I tell how?
Yeah.
So, like, consider, can you just write it in a list A union C, A union B?
Yeah.
Union C.
A union B, A intersection B, A union A intersection C, B union C, B intersection C. Yeah.
Like, okay. Like, you can see that we can subtract A intersection C from A union C to get the distinct elements of A and C, right?
Okay, A intersection B and
We can subtract A intersection B from A union B to get the distinct elements of A and B.
yeah, right.
Yes.
So if you
Now,
subtract that, you will get elements in A and not in B, right?
yes, like distinct elements. It will also have elements of B. It will also have elements of A such that none of them are equal.
Yeah, so like this you will get
Now we can compare this with A union C minus A intersection C and take the common of those intersection of those sets, and we can get that set to be equal to A.
okay. So here you will get in A and not in C.
Yes, yes. Just note that we can take common of those upper two and we can get the elements of A.
Yeah.
So for minimum three steps are required. I guess for 100, more than 100 are at least required.
Okay. Okay, so what you are able to conclude is for three sets, in three moves you can uniquely determine, right?
Yes, yes.
Okay, that's great.
Now, yes, yes. Now my claim is that at least 100 moves have to be made to know about those sets.
Okay.
At least. Like if we aren't making 100 sets, we are at least missing like at least missing one set in this step. If we miss that set to be included in the inclusion and exclusion, how will we know about those elements?
Wait, I didn't follow. So you are going to basically divide the sets in groups of 3.
No, like I'm saying, if consider that we are done in less than 100 steps.
Can everyone hear him properly? I'm not able to follow. Okay. So yeah, this is a very important step, a very important idea, and this is going to be extremely useful. Okay, how come 100 into 99 upon 2? I think that's a bit too much. You can do much better. Okay, what about the case where there are 4 sets? A, B, C, D.
We can do it in 4 moves, right?
For 4 what?
For 4 sets, we can do it in 4 moves, right?
Yeah, right. How?
We'll take A, B, and C. And then as we have shown for 3 sets, we can find A, B, and C in 3 moves.
Yeah.
Now we'll take any one of A and then do that move with A and D. So we'll have A in the union D and A in the section D. And
Yeah, now because like you know the set A, you can easily find the set B. Right?
yeah,
Okay.
Maybe you can induct on it.
Yeah, correct. Also, can you prove that for 4 sets, like 4 is the minimum and you cannot achieve it in 3 steps?
Like in 3 steps, you can at most achieve to get like those 3 sets.
Yeah, but like suppose
Okay, so my proof was as follows. Like consider for the sake of contradiction, consider that it can be done in 3 moves, right?
okay.
So in these 3 steps, at least one set will be missed in a pair.
Okay, bye.
Like if you consider any pairing, at least one set will not be in any of those pairing.
Like A, B.
No, wait. It
C,
is
D.
wrong. Yes, right. It is wrong. Indeed.
what we can say is if there are exact 3 or less moves, then there will be some set which has occurred like at most once. Like for example, in this case, the set A has occurred only once, or the set B.
Oh yes, but we can, and then we cannot get the form of A and B, right?
Yeah, so like the idea is okay. So suppose D occurs like at most once, or let's say exactly once. Then and now you have the remaining 3 sets A, B, and C. Now, in order to determine D, suppose like C and D occur, so you will have to first find C, and then in one move you will be able to find D. But then, if that is the case, and you are able to find all A, B, C, and D in 3 moves, then that means you are able to find A, B, and C in 2 moves, right?
Yes, that's a contradiction, right?
That's a contradiction.
Okay.
And so in this similar way, we can just induct. So suppose like it works for n sets. And for that, we are able to do that in exactly n moves. Now for n plus 1 sets, like suppose we are able to do that in n moves, then there will exist some element, some set say A, which has occurred exactly once. And in order to determine A, if it has occurred with B, then we should be able to determine all the remaining n sets in n minus 1 moves, which is a contradiction. And so what we have proved is for n plus 1 set, at least n plus 1 moves are required. And so now we have to come up with a construction where exactly n plus 1 moves are required. Like suppose n plus 1, or let's call it m. So suppose m is of the form 3k, then we can just divide it into groups of 3 k such groups, and we will be able to achieve that in 3k steps. Now suppose m is of the form 3k plus 1, then we will divide it in groups of 3, and then there will be just one more element which we will compare with any of the sets, and we will get the answer. And if it is 3k plus 2, yeah, then also we can do the same procedure. Like we can first find these like 3k elements, and then we have remaining 2 elements which we just individually compare with any element. And so for all the cases, we are able to achieve this construction in exactly n plus 1. So this is the minimum bound. Did everyone follow? Okay, so how do we get A, B, and C in 3 steps? Someone is asking. Okay, so the 3 steps are we find A union B, A intersection B, and like these 6 sets. Now, like we have to suppose we have to find all the elements in A. Now, if we subtract the sets A union B and A intersection B. Okay, so suppose we have to find some element in A. Now it can be in A and B, like it can be in A, B, C, all the three sets, or it can be in A, B, A, C, or it can be in only A. So we just have to determine what is the case. So suppose some element is in A intersection B, then we can definitely say that this element belongs to A. If an element is in A intersection C, we can say that this element belongs to this set. Now, if an element is in A intersection B, A intersection C, and B intersection C, we can say it belongs to A, B, and C. And now, if some element is only in A, then it should be in A union B, A union C, but not in A intersection B and A intersection C. Right?
Yes.
So like this, we will get the element which is only in A. And so in this way, we are able to find all the elements in A. And similarly, we will find elements in B and C. So yeah, did everyone follow?
Yes.
Okay. I will just give you some other problem.
Did you stop screen sharing?
Yeah, I'm starting it again.
Okay, no problem.
Like the thing is, I'm not sure we will be able to cover all the problems, so I will take the important ones first. Yeah, is it visible? Is it visible?
Yes, it's visible.
Yes.
Oh, so I wanted to ask one thing.
Yeah.
Like if some elf face says to LP that his hat is red, then does LFA tells to LP that his hat is also red.
Yeah, so what happens is, like suppose two elves A and B meet each other, then A will say B that your hat is red, and B will say to A that your hat is red. Like both will say that simultaneously.
Oh, so like they are telling each other simultaneously.
Yeah. Like it can't happen that in the morning A tells B and then in the evening B tells C. Whenever they meet, they just tell. Okay, from this statement, can you say anything about the hats of the two elves? Like, suppose now that okay, if an elf is wearing a red hat, I will denote him by R, and if he's wearing a blue hat, I will denote him by blue. So if two elves of the red color meet, then both of them can't tell that they are wearing a red hat because they have to tell they have to lie. So they will say that your hat is blue on the outside. And if two elves of the wearing the hat of blue color meet, they will have to tell the truth. So they will say your hat is blue on the outside. So they have to be of the alternate colors. So that the red one will say your hat is red and the blue one will say your hat. So the elves should always be of this combination.
Like consider elves A, B, and C. So if the time A and B tell to each other their hat is red, is the same time that B and C tell each other the hat is red, or they tell each other on different times?
Yeah, on different types. In fact, it can happen that when A and B meet, like A is wearing a red hat, and when A and C meet, A is wearing a blue hat. That can also happen. And an elf can change the hat more than once per day. So later on, he can again become red.
Can you consider the case n is equal to 3?
Okay. Okay, and maybe like you might misinterpret this problem. So the thing is, you have to come up with the situation in which the smallest possible number is achieved. Like
Oh.
it is not necessary that in every situation there is the same smallest possible.
This situation has to be like each of them has alternate colors. Like it is RB, 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 and so on.
No, like situation in a sense you have to find the initial configuration.
Yes, yes. I'm talking about the initial configuration of this.
Okay.
Like half of them have red, half of them has blue as the
Okay,
smallest
right.
number.
If you think this is the minimum one, then yeah, so like you have to find the situation and then how they are going to interact with each other.
Like first we need to prove that this is the minimum. Then we can easily count on that on
Yeah,
the second one. Yes.
yeah,
So like for n is equal to 3, the proof goes like if they aren't alternate color, then it means each of them have the same color, blue, 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 or red, red, red.
okay.
But if they do, so before meeting, at least one elf has to change its hat once
Yeah.
before any meeting.
Suppose this happens.
Yes. Then B and R can meet. Any R, B and R.
Yeah.
Yes. And then second meeting can happen in B and R again. The second in R. Now the third meeting has to happen between R and R.
Yeah.
So at least one of them has to change color, right? So it becomes two colors.
Yeah.
But in
So-
the alternate colors, you can just take RBR, which just reduces the step. You can see that we just reduce the step to alternate colors in here.
Yeah, right. So then these two can talk, then these two. So you will need only one change, right?
Yes, yes.
Okay. What about the case n is equal to 4? Is this the minimum?
Yes, it is.
Okay, how?
Like, consider it is not. So we can take like RRB, RRRB, all red or all blue, or 3 blue, 1 red. Okay. I'm not going to case bash. I'll just try to go slip through.
Yeah. Okay. Don't take case bash.
Okay. I'm not going to case
It's
bash. Okay.
basically 500.
Like you can just take the first 3. In the case, like we can take any 3 which have the same color at least, because and then we will need to reduce one step more. So which will be in contradiction.
Okay.
Like if there is no alternate coloring, then we can find at least 3 of them of the same color, and we can just take those 3 of them in a group, and we have to find that we have to get that at there has to be a change in color before any meeting between those 3. So it increases one step before getting this alternate situation.
So for the case of 4, this is the minimum. Like what about this case? Suppose it is like this originally. Now this blue can speak with all these red. Then after some time this red will become blue. Then it will talk with both of these. Then this will become. So we are able to achieve it in just 2 turns.
But those two are has to talk also again.
Those 2 are.
No. Works.
And in your case, in how many moves you are able to achieve that? Yeah, in your case also it happens in 2 moves, right?
Yes, it happens in 2 moves.
So let's first try to find this smallest possible number. And then the situation. Like, let's try it for smaller cases and then maybe try to find it for 1,000. Also, another observation is if there are 3 elves who never changed the color of their hat, then they can never say that your hat is red on the outside to all of them, like, right? So these 3 elves, suppose they never change the color of their hat. Now, if these two tell each other that your hat is red, so they are something like this. If these two tell each other that your hat is red, they should be like this. But then these two cannot tell each other your hat is red. So there cannot exist like 3 elves who have never changed their hat. Right?
So like in a group of 3 elves, at least one has changed their hat.
Yeah. And so what it means is that at least 998 elves should have changed their hat, or if there are n elves, at least n minus 2 elves should have changed their hat.
Yes.
So at least n minus 2 steps should be required, or 998 steps.
So then we can just do this by the construction of alternating colors, right?
Okay, how?
Like take n minus 1 of them to be the same color and the last one to be the distinct color, blue.
Okay, so suppose this is blue and all remaining are red, like this.
Yes.
Okay.
So like between these 3 red, like we have done all the steps with blue, red, blue, red. Now we need to do all the meetings between those red
Yeah.
L's, okay? So between any 3 L's, 3 red L's, we need to do like at least one hat change.
Yeah.
Yes.
Like there like at least n minus 2 elves should have changed their hat at least once. Okay, so suppose this is the original situation. Now what will happen is this will suppose become blue. Now he can again ask each of the elves. Now this becomes blue. He asks the elves, this becomes. So we are able to do that in 3 moves for n is equal to 5. So and now we have just shown that for n is equal to 5, 3 is the minimum number of steps, right?
We can then induct, right?
Yeah, or actually even no need to induct, just tell the algorithm like the situation for the minimum possible will be that one elf is blue and all the remaining elves are red, or vice versa. Now this first blue elf will ask all the other red elves and tell them that your hat is red. Then this elf will change the color to blue. all these will remain red only. And then he will ask all of them. And like that, it will become blue and red. And so finally, for n else, we will require n minus 2 moves. Like, except the first, like, from the second to the second last, all the elves have to change their hat.
Yes.
And so in this way, we have achieved a construction for n minus 2 steps. And we have shown that at least n minus 2 steps will be required. Like, now this is not necessary for like each and every starting configuration. You just had to find one configuration. So yeah, is the problem clear to everyone?
Yes.
Yeah. So some language has only 3 letters, A, B, and C. A sequence of letters is called a word if it contains exactly 100 letters, since that exactly 40 of them are consonants and other 60 letters are A. So what is the maximum number of words one can pick such that any two picked words have at least one position where they both have consonants but different consonants? So in a word, there are 100 letters. Out of them, 60 are A and 40 are B or C. And now, suppose we pick any two words. Then there should be at least one position where they have different consonants. Like here there is B and here there is C. So we have to find the maximum of such. Okay, so like, what is the maximum number of words? So suppose, like, consider this case that the first 60 letters are all A, and the next 40 letters are like some combination of B and C. And so there are in total 2 raised to 40 such combinations possible of B and C. And in each of the words, there is a distinct combination of B and C. So in this way, we can select at least 2 raised to 40 such words which have at least one position where they both have consonants but different consonants. So like the maximum numbers are 2 raised to 40 or maybe greater than 2 raised to. Any idea? So the thing is that 2 raised to 40 is the answer.
Like if it is greater than 2 raised to the 40, then there is at least one place in those 40 or those last consonants such that one A is there.
Yeah, but like
Yes.
this
But
is
in that but in that case, they will the last number which has the A in one of those last 40 place, it will not share this at least one position where uh, it has a different consonant with respect to another word.
sorry, I didn't follow.
Like if it is greater than 2 raised to the 40, then
Okay.
there is at least one word such that one of those A lies in the last 40 A position.
Okay. Yeah, otherwise, like, okay, got it. Yeah.
So we then get a random string of BC consonants, and one of those consonant has to be in the first 60 position.
Okay, so suppose B is there.
Yes. So like we compare this word to every other to the 40 words, right?
Okay.
Now see that it can't share like same position with 3 words.
B.
No, like this word can't share the same position of the consonants such that they are alternate with 40 words. 41 words, sorry.
Sorry, I'm not following. What you're-
Okay, maybe I will just try to.
Yeah, sure.
Goodbye. Did you stop screen sharing again?
You are sharing the screen, right?
No, I was saying that I will try to get a nice.
Okay, okay, sure. Yeah. Is the screen visible?
Yes,
my
it is.
screen
Yes, it.
Okay. Now this idea is like not very intuitive to come up with, so I will just tell you. So the idea is, suppose you are given some string like this. Now you just replace all the A's which are in the screen, which are in this string, with either B or C, any what, like suppose you replace this A with B, then this with C, then this with B, anyhow. So what you are going to do is, for so each such string of A, B, C, you are going to convert it into a string of only B and C. And so now how many strings of only B and C are there maximum?
To
2
the
raised to
100.
100. Yeah. So there are 2 raised to 100 strings of only B and C. And so like each string of A, B, and C, you can map it to 2 raised to 60 more strings, right? So like suppose there are m such strings, which is the maximum, then you are going to get that 2 raised to 60 m strings, which are going to be mapped to some element, some string of this type. And the claim is that no two strings are going to be the same. Like suppose we have some string 1 and some string 2, and we replace the A's in both the strings by B and C, and suppose we get the same string. Then what we will have is that wherever there is B here, there is going to be a B here. So it means that in these strings originally, there was never a consonant which was in the same position, but which was different. Like such a situation was never in these strings. So both these strings cannot belong to the set M, right?
Yes.
Yeah. So like maybe I will explain it a bit slowly. So suppose S1 and S2 are some strings of A, B, and C. Now we just replace the A's in the string by B and C randomly for string 1 and for string 2. And now suppose we get two strings which are exactly identical. So then that means that wherever there is a B in string 1, there is a B in string 2. And wherever there is a C here, there is a C here. So, but we are given that in the set we have selected, there is at least one position where there is a B here and a C here. And so this condition ensures that such a situation can never occur, that the two strings after replacing the A with B and C give the exactly same string or word, whatever. And so we get the condition that 2 raised to 60 times m is less than or equal to 2 raised to 100. And so m is less than or equal to 2 raised to 40. The answer. Did you follow? Like each string in M, you are going to map it to 2 raised to 60 such strings or words, which are made up of only B and C. And M is made up of A, B, and C. Okay, if you have not understood, just tell which part should I explain again.
No, it is clear.
Okay. So M is the set of the 2005 integers, and A is a subset of M. Then if for any AI and EJ belonging to A, so that I is not equal to J, exactly one isosceles triangle with these sides is possible. So find the maximum value. Like either a triangle of the form AI, AI, AJ, or AJ, AJ, AI. Only one of these, at most one of, okay, exactly one of these is possible. Okay, suppose AI is less than AJ. Now, a triangle is not possible if 2 times AI is less than AJ, right? Because we have that the sum of two sides should be greater than the third.
Yes. AI is greater than half AG, right?
Yeah, so
It is bounded.
yeah, so the condition is 2 times AI should be strictly greater than AJ. So suppose A1 is the smallest. Okay. So like we have A1 less than A2 less than A3. Then we should have 2 times A1 is greater than A2. Oh, sorry. We have that exactly one isosceles triangle is possible, right? So we should have this condition. Like the triangle AI is anyway going to be possible. And what we want is we want exactly one triangle, isosceles triangle. So we want if AI is less than AJ, 2 times AI is less than equal to AJ. So if A1 less than A2 less than A3, then we want 4 times A1 is less than or equal to 2 times A2 is less than or equal to A3, like this.
Where 2 times AI cannot be less than AJ if AI AJ exists.
Sorry.
Like if 2 times AI is smaller than equal to AJ, then the triangle inequality clearly does not exist for the isosceles AI AJ.
Yeah, that is what we want. We want exactly one isosceles triangle.
Like if we try to use this, only one of them can happen, not two of them can't happen simultaneously.
Yeah, so that is what we want. Like we want, if AI is less than AJ, we want the triangle AJ. It is like anyway going to be there. So we don't want the triangle AI AJ.
But it can happen with AI AJ also. Like if AI is greater than
Yeah, it can
AJ
happen,
by 2.
but we have to select the set A such that it can never happen.
Oh, yes, okay.
So can you try to find the bar? Like now, if there are 4 numbers, A1, A2, A3, A4, then our inequality will be like this. So you will need at least one number greater than it. Here you will require at least one number greater than 4.
At most 2 to the 10 elements can be in this set.
At most
2 to the 10.
2 to the 10. No, then you will get that n minus 1 is 2 to is 10. Like you will have 2005 should be greater than or equal to an, should be greater than equal to 2 times an minus 1, should be greater than equal to 2n minus 1 a1, 2 raised to n minus 1. And so what we get is n is less than or equal to 11 because 2 raised to 10 is equal to 102.
Yes. Sir.
Beyond that you cannot. And so mod of a is maximum 11. Now, can you find the construction?
Take all the powers of 2.
Yeah, very good. So if you take all these powers, then if you take the sum of any 2 powers of 2, then you will have like it is always less than or equal to the third. Okay, like if you take 1 and 4, then 1 plus 1 is 2 is less than 4. Or if you take 1 and 2, then 1 plus 1 is 2 is less than or equal to. Like 2 times 2 raised to I is less than or equal to 2 raised to j, where j is greater than or equal to I plus, right? And so this
Yes.
is the required set. So yeah, did you follow?
Yes.
Okay. Okay, this is the last problem, and then we will stop. There are a few problems which I was not able to cover, but like whenever I will share the whiteboard, you can see those problems and try solving them as exercise.
But this is the problem again. That one problem again.
What?
It's the same problem.
Oh, sorry, I copied it again. Yeah, I wanted to copy this. Find the largest positive integer a such that for any permutation 1, 2 up to 100, there are 10 consecutive terms whose sum is no less than.
Oh wait, it isn't like it would be the sum of first 10 numbers, right? Hello.
Hello, I didn't follow.
Like it should be the sum of first 10 terms. 1, 2, and 10. It is the minimum there.
Wait. So suppose this is some permutation. You are going to take the sum of first 10 terms.
Like I'm saying that A has to be less than or equal to 10, 10 in, 5 into 11, that is 55.
A is less than or equal to
55.
55.
Is it right?
No.
Okay, then I will try to improve this.
Okay, one simple thing. Suppose we add all the numbers. So that is going to be 100 into 101 upon 2 is equal to 5050.
It is
Now,
greater than equal to 10A, right?
yeah.
So A is smaller than equal to 505.
So like we can always achieve the value 505, right?
Yes.
Yeah. So 505 is always achievable. Now we have to come up with a construction such that 506 is never possible. Like if 505 is the correct answer. We have to come up with a permutation such that if we take any 10 consecutive terms in it, their sum has to be less than or equal to 506.
It is just PHP general principle. Like group them into groups of 10, then at least one group has to have like at least 505 terms.
There are some 10 consecutive terms whose sum is greater than or equal to 506. Like they can exist, right? For 505, we can use pigeonhole principle and say that yes, always there will exist 10 such terms. But for 506, pigeonhole principle would. So it means we have to come up with a construction so that the sum of any 10 consecutive numbers is 505, right? Like at most. So if we come with a construction like this. Check that it works. Like if you start from any odd number and take the next 10 elements, then its sum is going to be exactly 505. And if you start from some like even number thing, then the sum is going to be less than 5, because like the in between numbers are going to be the same and the 10th number is going to be less than 99.
Yes.
So in this way, we are able to achieve a construction where there are no 10 consecutive numbers whose sum is greater than 506 or equal to 506. So 505 is the answer. Did everyone follow? Okay, so I think I will stop now. It's already almost 8:30.